So this lectures on random vector. So like random variable, it's a random vector means there are number of variables, so more than one variables, random variables. So this is actually multi-dimensional random variable. So we let the probability space just omega and script f, and that p, the probability is fixed. Now this is in Rn. We defined in Rn. This we need defined in Rn. So what is the definition for the random vectors? The collection X, sometimes I like that, but we just avoid this. We just write X, no vector mark. That is actually a random collection of random variables, n many variables. N is a positive integer. So this x1, x2, xn is a random vector. We write that as X. Sometimes it's just bold X, bold is a bold like that, or maybe vector sign. And this is defined on, with this defined on is a multidimensional, so that omega, that script f, and this probability. And this defined on in Rn, this R to the n. So actually it's defined on the Borel sigma algebra on Rn. Now what is, we don't write that bold thing, we just write as X. What is X at omega? We know that like a random vector is a single random, it's x1. X1 is a random vector. It is actually from omega to R. But this is X is now omega to Rn, omega to R to the. So you take omega as small omega in omega, for all small omega in omega, we define x omega is like that, x1 omega, and then x2 omega, like that, xn omega. So this is the, it belongs to Rn. Remember, this belongs to R to the n, because each xi belongs to actually this, each xi is in this. So xi omega, x1 omega, x2, all are in real number. So it is real valued random variable. Each xi is a real valued random variable, and this xn is a real valued random vector. It is called real valued n-dimensional vector. It is called, this is called n-dimensional random vector. So I just random vector. RV maybe is random variable and random vector. So random. And again, what is the inverse image? Inverse image of an interval. So we just write as an interval like that. In one dimensional interval, like from A to B. Here is just interval like that. Say all x1, x2, n dimensional, n coordinate, such that each x's are in that minus infinity to say ai. So ai and ai in. So this is like intervals, collection of all in such intervals. So from I equal to 1 to n. So this is like intervals. N dimension is also called n-dimensional intervals. We should write that ai outside this notation. I equal to 1 to w. So this is an interval. So ai's are. So like say it is a for one dimensional, it is just if n equal to 1, then the interval means it is set of all such x or x1 such that this x is belongs to minus infinity to a1, so or a, like that. So it is just a minus infinity. It's open interval minus 1. For n equal to 2, this is just the interval like that. So x1, x2, and each x1, x2 are in say x1 is also of minus infinity to a1, and x2 is minus infinity to a2, like that. So this is like the interval. So what will be the visualization? So like in R1 is n equal to 1, it is just sorry, it is just not that, it is just, it is say it is a, so it is just this all the left hand portion of this a. For what about for this for two dimension say this coordinate maybe say this is say a1 comma a2. So this is actually this intervals. This intervals like that. This whole portion, this whole thing, whole part. So x a1 is from minus is a1 is actually x1 is less than a1 and x2 is less than a2. So any point here, any point in this region is actually if we take any point on this region x1 comma x2, then x1 is less than a1 and x2 is less than a2. Remember this boundary, that boundary is not belongs to the set because it is open interval. If it is a closed interval, then this boundary include like that. This a is not include, a is exclude. See here, this boundary is exclude. This portion, this whole portion. This in for the 3 dimension is just a model. You have to take the model in R3, and more than 3 dimension you can't visualize this. So this is the like intervals. Now this is all the intervals. And what is the inverse image? Now we know for the inverse image for say 1 dimension, we know what is the inverse image. Here it is inverse image of that I instead of all such omega in omega such that this x1 omega, we know for 1 dimension is x omega less than equal to a. Here it is less than equal to ai. If it's a closed interval, sorry, if it is a closed interval, then we have to take this. We put as a closed interval. So closed. So closed interval. So then it include this part include. Here this part include because it's a closed interval. So take that as a closed interval. If it's not include, then it is open interval. So here we use it as a, we take this as a inclusion. This a1 include and this x2 omega less than equal to a2, and order that xn omega is less than equal to a. So this is the inverse image, and this obviously belongs to this script f, this sigma algebra, and that is for all ai in belongs to. Now the theorem, the important theorem is this. So let x1, x2, xn is random variables on this omega script f and this probability function. Then this x, this random vector x1, x2 dot 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 xn is an n-dimensional random vector on this same sigma algebra, same this probability space. So same probability space. Now what is the proof? Proof is just straightforward. Take any interval, take any interval that x1, x2, xn, such that this xi is less than or equal to ai for I equal to 1 to n. Then what happens? Then this x1, x2 xn belongs to I. What is this? This is the inverse image of this. This is just the inverse image of this. So this is also a set of all omega belongs to omega such that this x1 omega less than equal to a1, x2 omega less than equal to xn omega is less than equal to a. So and now what is this? This is nothing but the intersection of all such thing. This is comma means it is just intersection. This is a comma, this actual intersection of all such omega in omega such that xk omega, or you can write xi omega less than equal to ak. So and for k equal to 1 to a, and that all the set, all this k for k equal to 1, k equal to, all these set are inscriptive, and therefore the intersection also inscriptive. So since it is inscriptive, we know if the inverse image of is inscriptive, then it is a random vector or random variable. Is the definition of random vector if for every interval, actually for every Borel set, the inverse image is inscriptive, but we know that if it is, we can prove it for every interval, the inverse image of every interval is even, then it is true for all Borel set. So this is the proof. Now next definition is like that for two variable. So we define a function. So like a distribution function. It is not a single variable, it is two variables. So we write dot comma dot. So you can write f x y is a variable, it is a distribution function, is a function. So how it is defined by, we define this function defined by this f of x y is just like in a one dimensional distribution function. What happened? It's fx is just probability of x less than or equal to x. Here it is just x less than or equal to x and y less than or equal to y. So this probability for all x, y in real. So it is just a function from R2 to 0. So the output is the probability and input is two variables x and y. So it is from R2. And this is known as a distribution function. So it's known as distribution function. It's a distribution function of the random vector, this random vector of x comma y. So two-dimensional random vector. Similarly, for the n-dimensional random vector, n-dimensional vector, this distribution function is f of x1, x2 dot xn is that nothing but the probability of x1 less than x1, x2 less than x2, and dot xn less than x, n-dimensional. Now, what are the properties of this function? Like single random variables, one-dimensional random variable, the probability using that probability definition, we can easily prove that the facts are this. We avoid this proof. We just write the fact. The facts are this: f is non-decreasing, like one-dimensional random vector, a random variable. This for it is true also for two-dimensional and also true for the n-dimensional random vector. So fxy is a non-decreasing, so it is increasing, and continuous from right, and right continuous function, right continuous. It is a number one. And number two is this: that limit x tends to plus infinity, y tends to plus infinity. This fxy is just one. It's one. And we write this limit. Sometimes we write by notation. Is this notation is f plus infinity plus infinity. We write this f plus infinity at this limit x tends to plus infinity, y tends to plus infinity. This is the notation. Sometimes we use this notation also. So the standard notation. If I write that f plus infinity y, that what is the meaning? That meaning is it is limit x tends to plus infinity f of x comma y. So y is fixed here. Similarly, for x comma plus infinity, this is limit x y tends to plus infinity f x comma y. So the notation this should be one. This is the and what the other is this: if y tends to minus infinity, that sorry, it is minus infinity, not infinity. Infinity is the plus infinity. If you write the infinity, that means the plus infinity. This is minus infinity fxy. This is 0, and the limit. No need of x tends to minus infinity, y tends to minus infinity. Just x tends to minus infinity, it is 0. Y tends to minus infinity, also 0. Both are 0. No need of taking the both things together. So again, by notation, what is the notation for that? Again, the notation is this: f of that x comma minus infinity. This is just limit y tends to minus infinity f of x comma. Similar notation for that next second one, that f of minus infinity comma 1. This is f limit y x tends to minus infinity f of x comma. This is the notation, and this both must be 0. For this is true for all x, and this is true for all y. What is the idea? The idea is this: you just see this. What is this? So if you take x comma y, say x comma y, this is x comma y. Now with this, the probability of this whole thing, whole path. Now as you go x tends to infinity and y tends to infinity, that means this whole thing goes to take the whole this increased, this x part and y part both are increased. This is increasing, and since both x tends to infinity, that means is actually in limit this takes whole R2, it's a complete whole R2. On the other hand, if you take fixed x, if you take fixed x, so you take fixed x, and then y tends to infinity, what happens? What is the meaning of that? Meaning is this. So for this part is that f of xy, this probability, this part probability of this the region. But as y tends to minus infinity, that means it goes down. But x is fixed. This line is fixed. This horizontal line actually go down. That means this is squeeze all this area. This actually going to the limit is actually 5 cent. No need of taking both the x and y tends to minus infinity. If you fixed y, if you drop down this x tends to minus infinity, this actually goes to the minus infinity, 5 cent. Similarly, if you fixed x, if you fixed y, and if you just drop that vertical line to the left side, that x tends to infinity, that y is fixed, still this goes to the 5 cent. So that's why the probability is 0 in each case. So it is just an idea. No, it is not a rigorous proof. We need a rigorous proof. That proof you just consult any book. What is the proof? So we just omit the proof here. And one example is this. The example is, say f is a function of two variable now. So it is a function of two variable, function of two variable. Defined by, so f of xy is 0, 1, 0 if x less than 0, or x plus y less than 1, or y less than 0. So then this is 0. Otherwise, it is 1. So this is a function of two variable defined like that. So either x0, x less than 0, or y less than 0. Anyone? So x less than 0 means this portion. Y less than 0 means this portion. So second quadrant, third quadrant, fourth quadrant, everywhere the function is 0. Also, if x plus y less than 1, what is the x plus y less than 1 region? This is the x plus y less than 1 region. This portion. This line is x plus y equal to. So this portion also, this part also 0. So the whole thing is this part also 0. This quadrant, that second quadrant, fourth quadrant, third quadrant, and including this part. So from the first quadrant, this part is 0. Otherwise, it is 1. The function value in this region is 0, and the white region, this is 1. This is the idea. This is the definition of the function. This is the function f. Now then x satisfies both all these facts for the distribution. It is non-decreasing, it is increasing function, and it is as x tends to infinity minus infinity 0, y tends to minus infinity 0, and is xy tends to 1, both tends to plus infinity, then it is 1, because it's in the white part. As say x greater than 2 and y greater than 2, then it is you are in the white part, and then its function is 1. So this is a two-dimensional distribution function. Oh no, it may not. It is not a distribution function at all. It satisfies both the. Sorry. So this is actually the necessary condition. These conditions are necessary, but not sufficient. For a distribution function, this is true. But if this is true, it may not be distribution function, right? So this is an example of function which satisfies all this condition of distribution function, but still it is not a distribution function. Why? Why this is not a distribution function? The idea is this. So what will be the probability of say minus 1 by 3 between 1 by 3 to 1, and say 1 by 3 to 1 for y also 1 by 3. So what is the probability? Now, what is 1 by 3? Where is the 1 by 3 part? This here is the 1 by 3. say 1 by 3, 1. This is 1 by 3, 2 by 3, 1. So this point is actually 1 by 3, 1 by 3. Now we want to find the probability when x less this portion. X is between 1 to 1 by 3 and this point, this interval, right? We want to find this probability of this region, interval in two-dimensional interval. So what will be the probability? Now what is this? This is just f of 1 1 plus f of 1/3 1/3 minus f of 1 comma 1/3 and then minus f of 1/3 comma 1. This part is actually this. You can easily check that. So this is 1 comma 1. F of 1 comma 1 means this whole region. Then minus this part, we'll get that thing. If we minus this is just 1 comma 1/3. So if you take f of 1 1, f of 1 1 is just this whole thing, this whole part, this whole thing, minus f of 1 comma 1/3. F of 1 comma 1/3 means this part, so you will get this part. Now if we add plus f of 1/3 1/3, this part is actually, this is 1/3, so you will just add this thing. So it is actually this and this, and then minus f of 1 comma 1/3, sorry 1/3 comma 1. You just take this is point is 1/3 comma, so you just minus this, so you just this part, you'll get this part. Now what is this? This is 1, this is 0, this is 1, and this is 1. So this is minus 1. How this probability can be minus 1? It's strictly less than 0. So it is not a distribution function. It's not a distribution function. But it is it's not a distribution function, but it satisfies all these conditions. It satisfies all these conditions. Okay. So what is the extra thing we need? We need this part. We need this condition. So this is not a distribution function, but satisfies the two conditions, but still it is not a distribution function. Now let x1 is less than x2 and say y1 less than y2. Here it is 1/3 less than 1 and 1/3. We take x1 y1 as a 1/3 and x2 y2 as a 1. Now what is the probability of x in this 1/3 and 1? Say like x1, x between x1 and x2 closed. Similarly y1 to y2 closed. And this is actually we have this f of, we just similar way, this similar thing. It is just a point. We need this part. This point is actually x1 comma y1. This is x2 comma y2, and this is actually x2 comma y1, and this is x1 comma y2. Now this is the you can easily check the similar way. This is f of x1 comma y2 minus f of x1 comma y. This is x2. This is f of x2 comma y2 minus f of x1 comma y1 minus plus f of x1 comma y1 minus f of x2 comma x2 comma y1. And that must be greater than equal to 0. This is a condition. Extra condition we need. Only this extra condition. So we need this a third condition. You can take as the third one. This part as a third one. So this thing, this condition as a third one. We just write. This is the third one. It's a third condition. So not only that 3-2 condition, we need one more extra thing. In one dimension, this third one is not needed because it is for the one dimension is monotonically increasing means automatically x1 less than x2 is then f of x2 minus f of xn greater than equal to 2 automatically because it's non-increasing, non-decreasing. But here the function is non-decreasing does not satisfy that may not be this condition hold. We need the extra thing. The third condition is this: for every x1 less than x2 and y1 less than y2, this thing, this f of x2 y2 plus f of x1 y1 minus f of x1 y2 minus x2 y1, this part is greater than equal to 0. Now we'll prove that. So for one dimension, this one that two condition is sufficient, necessary and sufficient. But multi-dimension, this 1 and 2 is not sufficient. This is necessary, but if you take the third one, that there's three conditions, that limit thing 1 1 0 0 and then this non-decreasing thing and this third one, this all together, if f satisfies all these three conditions, then f is a distribution function. We can prove that f is distribution function. We just leave this proof, we omit this word, but we can prove it. You can consult the book. So next definition is this: a two-dimensional random variable, say a two-dimensional random variable, random vectors actually, x comma y, is said to be discrete type. Is said to be discrete type. Discrete type, like in one dimension continuous discrete, it's discrete type if it takes on pair of values belonging to a countable set, like one dimension, it's countable set of pairs A, the set like a name as A with probability 1. In a countable set is with probability 1. Then it is a discrete type, like one dimension. And we call this every pair, that the pair, we call every pair x comma y, that xi comma yi, that all pair, all set of the countable collection of that pair. Each pair we call as a that is every pair that is assumed with a positive probability, that is, or it's a positive probability, say Pij, we write that is Pij, this is a positive, Pij is positive probability. It's called a jump, it's a jump, like one dimension is called jump, is a discontinuity point of discontinuity. Here this distribution function is discontinuous, it's called jump point of the distribution function of that x comma y, random vector x. And this, and we call that thing, that Pij, that probability Pij, and the jump we call jump at we call this a jump at xi comma yj, call that. And I from 1 to infinity, j also from 1 to infinity, and this may be finite random variable is finite, it may be countable. And what happened, that like the sum of the probability must be 1. Here also sum of the probability 1, and this summation Pij, sum over I and j, that must be 1. That double series, this is called the double series, like a single summation ai is 1. That is series, and this is called double series, like double series, double sequence. And what is this? Why this is true? Because if actually the fxy is the distribution function for and f is the distribution function. F is distribution function of this xy random vector, two-dimensional. Then fxy is nothing but the summation over all this bij in the set B. What is B? The B is nothing but the collection of all such xij such that this xi is less than x and yj less than or equal to actually yj less than or equal. So this is the distribution function and discrete, and we similarly for the PMF like probability mass function. Here also we have this probability mass function for 2, and this same thing is for true for the multi-dimension. And the definition 4 is this for the let xy be an random vector of discrete type, two-dimensional, that takes on pair of values y, xi, yj, like y I want to dot and j. It may be finite. It may be finite. We call that pij, that function pij. Therefore, every I and j, it's actually for different ij, we get different pi pj, pij, that x equal to xi, for to x equal to xi and y equal to yj, and I and j are from this. It may be finite actually. It's called the joint probability mass function. It's called joint. We know that it was something joint, marginal, conditional. This is a joint basically. A joint probability mass function of this. So this lecture up to this, then next lecture we continue with continuous random vector and some example. This is for discrete.